So man in a lift and apparent weight, what has it mean and how does it feels? That means when we say about weight is equal to normally m into g, but here g is the acceleration due to gravity of any planet or any place. So normally the weight is equal to m into g, the acceleration due to gravity, but in the specific case of a man in a lift, that means let's have a look at the situation. Here we have a lift, and at the bottom of lift we are putting a weighing scale, and the man is standing on the weighing scale. This lift is at rest now, so the weighing scale will have a reading of mg, because mg is currently acting on it. A man is pressing it downward, and the floor of lift will provide the normal force to this weighing scale, which is in the upward direction. The acceleration is 0. Now the acceleration is 0, that means the net force on scale is equal to 0. So F net is equal to ma is equal to 0 is equal to mg minus normal. That means the normal is equal to mg in this case. The value of normal force, the magnitude of normal force will be equal to the mg force at the rest condition. Okay, but the problem occurs when this lift starts moving. The lift starts moving, the man feels there is a change in its weight, because when we are standing in a lift and the lift starts suddenly, we observe that our legs bend. Our legs bend, that is due to the apparent weight, because our body is instructed to handle the weight of our body. Let's say if we have weight of 500 newton, so our muscles are instructed, our legs are instructed to bear the weight of 500 newton. But when the lift starts, our weight gets changed because of this apparent weight, and our body is not instructed to bear such weight, let's say 600 newton. So our legs gets bent. Okay, so the change of 500 newton into 600 newton, it is called apparent weight. And how it is getting changed, we will discuss about it. And this is actual weight. So actual weight gets converted into apparent weight, and because of this we feel abnormal weight of our body. Let's say our legs gets bent, or when it goes downward we feel something light. Okay, so in case 1, here we will learn about some cases of the motion of lift. In case 1, we will see a lift is at rest and going upward. With the acceleration A upside. Okay, lift is going upward with acceleration A. Let's draw it. Lift is having acceleration A. A person is standing on a weighing scale as usual. Now, when we look at the weighing scale reading, the weighing scale has a free body diagram, something like this. The person will have mg pressing it downwards, mg, and the normal is being offered by the surface. So the normal force is equal to mg in the opposite direction of mg, and the whole system is having the acceleration a upward. So it is the condition of, let's say we have a 10th floor building and we are at the ground floor. So the lift is going to first floor and here it is 9th floor and we are going to reach at 10th floor. So let's have a look at this condition. The lift is at ground floor, it is at rest. Now it is going upward with acceleration A. So what happens in the lift case? It is starting at v velocity 0. It will go to the first floor with acceleration A and after that it will attain the v velocity. It is constant till the 9th floor and v here is constant. From first floor to 9th floor its velocity is constant, it is moving with constant velocity. That means it has the acceleration 0 meter per second square. Now at the 9th floor it will have some velocity v which is same as the velocity attained at first floor, but it has to stop at the 10th floor, so it will have a retardation which is in the opposite direction of motion. So it has acceleration from ground floor to first floor upward acceleration, and first to 9th floor it will have a constant velocity, and from 9th to 10th it will have retardation. So we are considering case 1 where the lift is going upward with acceleration A, which is the case of ground floor to first floor moving. Okay, so let's observe the free body diagram. Here this free body diagram, here upward force is greater because when it is moving upward, that means upward force is greater than downward force because motion is upside. Okay, so upward force is greater than the downward force, that means N is greater than mg. So when we write the equation N minus mg is equal to net force ma, here N is equal to mg plus ma, that means m common a plus g. So the normal in this condition n1, let's say n1 is equal to mg plus a, which is greater than mg, and it is called apparent weight. So here W apparent is greater than W actual, which is g plus a, and actual weight was mg. So in the first case, when the lift is starting from rest position and attains velocity v, the accelerated motion in the upside direction, the apparent weight will be greater than the mg. That means when we push the button to reach the 10th floor, our legs gets bent, and the reason is the apparent weight becomes more than the actual weight of the body. Okay. Here in this question, a man in a lift which is going upward with acceleration of 5 meter per second square will observe the change in its weight by how much Newton. So a person will observe some change in his weight, and we are going to find out the how much Newton its weight has changed. So let's make a clear picture of it. Lift is going up with the acceleration of 5 meter per second square. Let's make a free body diagram. Person has a weight, let's say mg. The normal force is upward and acceleration is 5 meter per second square. So we have seen the apparent weight, which is equal to m into g plus a, will be equal to m. The g has a value of 10, let's say 10, so 10 plus 5, that is 15 m, 15 m Newton. So its apparent weight is 15 m Newton, but its actual weight, the person has actual weight mg, which is equal to 10 m Newton. So change in weight is equal to W apparent minus W actual, that is 15m minus 10m, it is equal to 5m Newton. So the person will observe 5m Newton of change of its weight. Suppose if it has a mass of, let's say 50 kg, if he has a mass of 50 kg, then the change in his weight will be equal to 50 multiplied by 5, that is 250 Newton. Okay, so 250 Newton of extra weight will be on his foot or on his legs. So this much amount of extra weight on his legs because of the motion, upward motion of lift. Okay, due to upward accelerated motion. Now let's see a case which is the lift is moving with constant velocity from first floor. So let's case 2, lift is moving with constant velocity. Lift is moving with constant velocity. Person is standing on the weight scale. The velocity is constant. This is the case of first floor to 9th floor journey. Okay, first floor to 9th floor, acceleration is 0 and the lift is moving upward. So we can imagine this condition and we get easily. Let's say mg is downward, the downward force is n, but the acceleration is actually 0. The acceleration is 0, that means n is equal to mg, so W apparent, its apparent will be equal to actual weight. Okay, it will be actual weight. That means there is no change in his weight. Let's have a question. Suppose a person in a lift which is going downward with constant velocity 2 meters per second, what will be change in his weight in this condition? Okay, so here the apparent weight will be same as actual weight, no matter it is going up with velocity v or going downward with velocity v. In both the cases the acceleration is 0. The acceleration is 0, that means there is no change in its weight, so we will have the answer of 0 Newton. 0 Newton change in its weight. Okay.